Right, so similar figures, okay, is a little bit different to your congruence. Okay, similar is not exactly the same. Okay, similar is a little bit different, but they share some qualities about them that make them a little bit the same. Okay, so when we look at similar figures, it's not the same as congruent. It's slightly different. Okay, for example, let's see. Me and my dad are both similar. We're not congruent. Okay, he's got a bigger belly than I do. Okay, he's a little bit shorter. Okay, we share the same frame. Okay, but we're similar. We're not the same. Okay, whereas, for example, if me and I had a twin, we would be congruent. Okay, so similar just means not the same, slightly different, but you still share similar qualities. Okay. Alright, so our intention today is to understand figures that are similar and also understand the corresponding angles or the sides that they have similarities with. So for example, if this side of the triangle is AB and this side of the triangle is XY, AB and XY are similar even though XY is a bit bigger. Okay, so they have corresponding sides, for example, and understanding the ratio of whether they've been made bigger or smaller. Also, we're going to try and understand our scale factors. So this is probably something new that you've never done before, or maybe you have. Okay, but understanding your scale factors and how they work. Okay, there you go. Scale factors, okay, between two different figures. And then being able to use that scale factor, whether you've maximized it or minimized it, to understand or find the missing link. And as a success criteria, you will be able to find sides of unknown sides of different shapes. And look, one of the practical examples of this is, say for example, you wanted to measure the height of the Empire State Building. Although you can Google it, yes. What you would do is you'd have like a scale model of it, okay, and then you'd understand how much in scale is the Empire State bigger than the original scale model, and then you'd multiply it to find the height. Or, for example, maybe you want to figure out the height of a tree, okay? And you have a scale model of how big like a small tree might be, and then you would use the scale model's height and multiply it with a certain number to get the height of the tree. All right? All these things, have some practical use. Okay, so that's what we'll be using the scale factor to find lengths and side lengths of certain triangles in this case, because we won't be really working with other shapes. Now let's think back to last week when we started this topic, our inverse operations. Yeah, we're going to use these again. Okay. So if you have a plus or an operator of plus on this side of the equal side, when you move it to the other side, its inverse or its opposite is minus. The inverse of minus is plus. The inverse of multiply is divide, or it looks like that too. Then the inverse of divide is times. The inverse just means the opposite. Right? So some quick examples here. Here you've got x over 3 equals 5, and you want to make x by itself, so you're going to inverse that 3. It is a divide by 3, so when you move it to the other side, see how it becomes times. Okay? And that means x equals 15. Okay, so I want you to do this one. Solve x for me. Isolate the x to make that by itself. So what do we do?
X
Equals
5.
Yes. Yeah, all for it. Alright, so I'm going to ask you guys how you do it. Alright, so for this equation here, what do we need to do? What are we getting rid of? Okay, I'm going to ask Regan, because he's good at this. Regan, I want to make x by itself. What do I move? 5, good. It's divided by here, so what am I doing? If I bring it to the other side, Regan, it becomes times, good. So what's 7 times 5? What is it, guys? 35. So x equals 35. Easy. Okay, nice and easy. So that's what happens when we need to do these sort of equations. And you'll come across it when you do the scale factor questions. All right, this one here is slightly different. Okay, if it's 6 over x equals 4, okay, to solve this, all you need to do is swap the unknown with the number on the other side. Okay, you'll come across it a few times. Right, so swap that number unknown with the number on the other side, that letter in the unknown with the letter on a number on the other side. So here you've got now 6 divided by x equals 4. This is a divided by, but all you got to do is swap it with the 4. So that takes its spot, and x is now here.
So how do you know you have to do that?
When you get a question like this, where the unknown is on the bottom.
But isn't that the same as just like,
As?
wouldn't you just be like, oh, I have to times something? Like,
Not quite, no. Generally with these ones, you just have to swap that x with a 4. And the way you would justify that is, think about it this way. This one is 6 over x equals 4, okay? Normally what you would do, you should go, so get rid of that x, it's divided by x, so here it becomes times x, yeah? So you're left with 6 equals 4x. Now what do you do? Yeah, divide 4. So now it's the same as basically this, 6 over 4. So all it's done is you're just swapping the x and that 4.
Would you do the same thing if it was 6x plus something equals something?
So we'll try that. I'll show you that in a second. All right, but let's do this one for now. Okay, how do we solve this? Well, that x and that 5 swap places, so now you're left with 10 over 5 equals x. That's just basically saying 10 divided by 5. Okay, so x equals 2. Okay, so I'm going to insert a page here, and Michelle is asking. So you're saying, Michelle, if the equation was like 2 over x plus 3 equals, I don't know, like 7. Okay, let's go with that for now. Yeah. So in this case, what you'd get rid of first is that plus 3. Okay, you bring it to the other side. So it's plus 3 becomes minus 3 here. So you're left with 2 over x equals 4. Now what do we do? Just swap the x and the 4. So you swap these two, so you get 2 over 4 equals x. And you swap x equals a half.
simple and perfect.
Yeah. Right, so that's maybe another form of it you might come across. But yeah, if it comes, I'll go through it again with you guys. Alright, let's go to the next page. So, like I mentioned before, when shapes are different size, so not exactly the same but different in size, so the same shape but just different size, we call them similar. Okay, similar because again they don't quite share exactly the same thing, but there's something about them that's still the same. Okay, similar shapes normally will have the same angles. Okay, they always have the same angles. However, the thing that's different is that their sides are not exactly the same. So for example, here the corresponding side of AB, where would that be here, guys? So what's the corresponding side for AB?
DE.
DE. Okay, this side. See how they're corresponding, but they're not exactly the same. Okay, so what's happened is it's scaled down. Okay, so the scale factor has decreased it. Okay, so in terms of writing down a statement of how we say they're similar, this is what we use now. Notice how it's triangle ABC is squiggle, which is similar to triangle DEF. It's no longer equal sign. Okay, so when something is similar, we use a squiggle sign. This guy. Okay, it's not the equal sign anymore, only the squiggle. Okay, so that's some things to think about. When you have similar triangles, angles are always going to be the same. That's fine, but the corresponding sides will either be bigger or smaller. That's the difference. Okay. So scale factors. Now, with similar shapes that are different size, to actually understand, okay, what's the difference between them, we need to know what we call the scale factor. So this formula up here, really important for you guys to know. Okay, this. Okay, you need to know this. how do you calculate your scale factor? So the scale factor tells you how much something has gone up or down by, or how much something has been enlarged or minimized by. Okay. Let's see if there's an example here. Like say for example, if you compared me to me and then baby me, okay, what's the scale factor there? Okay. You're trying to figure out how much did I increase in size by. Okay. Or if you try to compare maybe a toy truck to an actual truck, what's the scale factor there? So you're trying to figure out how much is the toy truck enlarged by to get the original, the actual truck, or vice versa.
So
Yes.
you're saying that you divide your length of height now to your baby's height.
Well, that's not necessarily how we calculate that, but yeah, similar in terms of principle. Okay. So to calculate the scale factor, a good thing you brought that up, is the new length of the corresponding side divided by original. I like to just minimize it as new divided by old. But if we went with Lily's example, if I was like, I don't know how big I was when I was a kid, 30 centimeters, so like that when I was a baby, and now I'm like 150 centimeters. So in terms of the scale factor, so if I am currently 150 centimeters and baby me was 30 centimeters, the scale factor is 5. I got 5 times bigger. Yeah, does that make sense? If baby Ramia was like 10 centimeters,
I was like
50. Sheesh. Okay. So for Ramia, if he was originally 50, and Ramia, how big are you now, height wise?
186.5.
Whoa, 186.5. So 50, 186.5. Okay. So in terms of his scale factor for his size, 186.5 divided by 50 centimeters. So you can see scale factor for Amir is 3.73. A little bit smaller, but that's because obviously he was the bigger baby than Mr. Toya. Okay. And he's obviously a little bit taller than I am. Okay. So understand this, scale factor, I like to make it shorthand by going SF, scale factor equals new divided by old. Okay, now what do I mean by that? If, say, for example, you've got this shape, and it's now been enlarged, so this is the original or the old shape, and this is the new shape, all you have to do to find the scale factor is look at the corresponding sides. So I see this corresponding side is corresponding with this. So if this is my new shape, the scale factor for this would be 4 divided by the old length of it, which is 2. So the scale factor there is 4 divided by 2, which is 2. Okay. And the same result can still be achieved if another pair. Okay, we don't need to know that too far, but that's fine. Do we understand that? So that's how we calculate your scale factor. So the new divided by the old, or new divided by original. Okay. Here is an example that we can use. So we've got this shape. Triangle ABC, triangle A dash, B dash, C dash. Okay? And we're trying to figure out what is the scale factor, which it's already done for us, but then we're going to try and find the lengths as well. Okay? So in terms of the scale factor for its enlargement, it's going to be the new shape. So the corresponding length here is length A to C, and it's corresponding with A to C. So this is 9. So that'll be 9. So the new divided by the original, which is 3. So the scale factor is 3. Okay. Now let's say hypothetically, for example, this length is 1, that length is 2. Okay. I want us to try and figure out what would these lengths be. Okay. So if the scale factor is 3, meaning it got tripled, so to go from this to this, it was times 3. For the scale factor, what would this be?
1 times 3.
Good. So this length, okay, multiplied by 3 will give us this length. So that means this length should be hypothetically, it should be 3. Okay? This side length here, if this length was 2, and to go there, you're timesing it by 3, what would this length be? 6. Good. So that would be a length of 6. Okay? Because everything has been tripled, multiplied by 3 as a scale factor. Alright, let's do some of these as an example. For this shape here, we have to calculate the scale factor and then find the unknown side of x. So we have triangle A, triangle B. Okay. Now, can anyone tell me what are the two corresponding sides here? For triangle A, you've got which side? Bottom. And what does it correspond with? The bottom here. Okay. And also for triangle A, it's got a corresponding side here, as well as this side.
How do you know which one's the original?
Well, normally I treat the one on the left as the original, and then the thing you're looking for is the new thing. Okay, so whatever you're looking for, treat it as the new. So here, scale factor, remember, equals new over original, or you can call it old. It's up to you. So in this case, my new length, okay, I have to look at the corresponding sides here. This is 15. So in this case, it'll be 15 divided by the original length used to be 5. Therefore, the scale factor is 3. Right? That means length x over here, unknown side, x would be equal to the scale factor of 3 times this side here, 3.
9.
Correct, which is 9. So x must be 9, because it's being tripled in size. Okay. Let's do another example. Oh, one more thing. Notice how if you have a scale factor that's bigger than 1, okay, this is something you need to think about. If you have a scale factor that's bigger than 1, it's going to get bigger. Okay, if your scale factor or your number is going to get bigger. But if your scale factor is less than 1, it's going to get smaller. Alright, so think about that. Let's try this. So now we have this shape here. Okay, we have 2 triangles. It's given us more information, which is really good. And we can see that that's angle A or BAC. That's angle ACB right here. And then we're looking for this length, AB. No, A dash B dash. Alright, so in this case, if you're looking for A dash B dash, start with the scale factor. Okay, it's original or new over the original. Okay, so in this case, when Lily asks, how do you know which one's new, which one is original? Normally, I always treat this new shape as the one that you're looking for, the unknown length. Okay, so that's my new shape, and this is my original shape. In this case, right? So I can see now it's getting smaller. Okay, the scale factor is going to be a number less than 1, or a fraction. So in this case, my new length, okay, is over here on my new shape, and I have to find the corresponding side. I can see that this side, A dash C dash, is corresponding with AC. So that means here, if that's 2, for the new length, the original of it was 4. Therefore, the scale factor is a half, or you could also say 0.5. Okay, which means that x, this length here, is going to be 0.5 times that length, which is in this case, this one here. Okay, because we're trying to look for this. Okay, so that means to go from 4 to 2, this was multiplying by 0.5. That means to go from 9 to x, also multiply by 0.5. Right, so 0.5 times 9 equals 4.5. Okay, so that means x is 4.5 or half as big as it used to be. Okay. We understand, guys? We need to do one more example. So maybe I'll do one. We'll do one more. Okay, one last one. We have space. All right. So let's say you have this triangle. Let's get a baby triangle. A, B, C. Okay. Okay. So you have that. And you have these angles here. Remember, with any triangle, the angles are going to be the same for similar triangles. Okay. Alright, so here, let's say that this is 10. And actually, yeah, we'll go with 10. And we want to find out what this is. But this was 6, and now this is 3. Okay? Let me just fix that. Okay. 6, and that's 3. Okay? So one more example here. So figure out the scale factor. Remember, it's mu divided by the original. Okay, the scale factor in this case, I can see the corresponding sides would be the bottom one, so DF and AC. So that would be 3 over 6. So the scale factor again is a half. Okay, and then to figure out X, which is this one, it's corresponding with this. So that means X should be a half times 10. That means X is 5. So the length of X is half as big as it was. Alright? Cool. Alright. That's it for me. I'm going to stop.